Hi everyone, I just wanted to talk to you a little bit about modeling the behavior of gases, or we can also call these fluids. Basically, these are things that react to that will react to a flow, right? That can flow and will react to a force. So another title for this might be, another title for this might be maybe your chem prof had it right. And that's because we're going to talk a lot about the kinetic molecular theory of gases. This is something that they emphasize heavily in a chemistry course, and the basic idea is this, that we can describe the behavior of gases by thinking about them in a very simple way. We can think about them as hard spheres which fly around. Think about them as hard spheres which, one, fly around, and two, collide with each other. Collide with each other, container, etc. And this will allow us to describe all sorts of properties of gases, and it turns out we can use this same model to talk about fluids, which fluids can also include liquids. It can also include other things that just don't quite fit in, don't quite fit under the category of solids. You'll notice these are hard spheres, so this is kind of like the ball and spring model we talked about for solids, but there's no springs. All right, so without much further ado, so one of the properties of fluids and gases is that we can define something called the pressure. And this is something you've absolutely heard about in chemistry class, and we want to relate it to the force that is exerted on an object. So, for example, if I have the reason that a balloon deflates is air leaves the balloon, it diffuses out, and the pressure inside is no longer equal to the pressure outside, so the volume shrinks, right? And you can think about that in terms of your friend Pivnert. Right? If N goes down, volume goes down, as long as we're keeping the pressure constant and the temperature constant, and so on and so forth. All right, so the first thing you should probably do when you look at this expression, that force is equal to pressure times area, is say, one, area is a vector. And sure, it's a vector. I mean, you can have a surface, some sort of flat surface, and what we want is to be able to describe how this surface is facing. And so the area vector, it points perpendicular to the surface itself. And its magnitude is the area. So why not call it a vector? And so this way we can say that the force is always going, that the force some fluid applies to a surface is always going to be perpendicular to the surface, right? So the pressure that air is exerting on the wall is going to be into the wall. The pressure air is exerting on the floor is going to be down. The pressure air exerts on the ceiling is going to be up. It's just perpendicular to that surface. The second thing that we should think about is, okay, what are our units? And the units of pressure, the SI unit of pressure is called the Pascal. which is abbreviated PA, and it is equal to a Newton per meter squared. So if I have an area is 10 centimeters squared, I'm going to need to do some conversion if I'm given a pressure of 5 pascals. We're going to need to do a conversion before I multiply so I get this area in terms of something reasonable. Oh, and 5 pascals is a tiny pressure. If you remember, atmospheric pressure is something like 101 kilopascals or 101,000 pascals. So this is the atmospheric pressure. That's one of those numbers that you have seen before and can look up on Google whenever you want. So let's think about the forces on an object in air, okay? And so we would expect that pressure, like we said, it's due to all these microscopic, well, it's a property of a fluid, right? But it's due to all the microscopic collisions of air molecules banging into the walls of this container, right? So tiny little air molecules are banging into the walls of this container, exchanging momentum with it, and thereby exerting a force. So what we can say is that if we want to, we can think about all the forces on this object as being the pressure at the sides times the area of the side. And the same thing over here, the pressure of the side times the area of the side. And we know that the pressure at the bottom will be times the area of the bottom. And the pressure of the top times the area of the top. These are all the forces. These are all the forces related to the pressure that we expect. There's one other. If this is some solid object, whatever this object is, it's got mass. So we would expect that there is the mass of the object times gravity. One last thing. Let's make this a rectangular cube. So I'm just going to say that the area of the top is equal to the area of the bottom. And because I don't want to keep writing top and bottom, I'm going to call this A. The other thing I'm going to do is say that this cube has some height h. So if I write down Newton's second law on this object, I'm going to get that the pressure on the bottom times the area minus the pressure on the top times the area minus mg will equal the mass of that object times its acceleration. Now right now I've just said I've got some square object. Well, what if I said this square object was a box of air? With no boundary. And so if it's a box of air with no boundary, it's still got mass. And that mass is going to be equal to the density of air, or whatever fluid it is. It could be a box of air, it could be a box of water, it could be a box of oil, it could be a box of something else. Anything that's a fluid. The mass of that will be the density of the mass of this box will be the density of the air times the volume of the box. So in terms of the parameters we've defined, this is just going to be the density times the area of the top and the bottom times the height, because this will be the volume. Also, this acceleration ought to be 0, because if we just have a bunch of static air, it's not going to be accelerating up or down or right or left, it's just going to be sitting still. So we can write down that the pressure at the bottom minus the times the area minus the pressure at the top times the area minus the mass, which is the density times the area times the height times g, should equal 0. Area drops out. And we are left with a relation that looks like this. Pressure of the bottom equals pressure of the top plus rho GH. And it turns out that this sort of matches our intuition for what's going on. We learn here that pressure increases as you go down. Here I've changed it from a cube height h to something with a depth d. And it really doesn't matter. It actually turns out that if I have a fluid, any sort of container, that, let's say it's holding some liquid, and if I know the pressure at the top, and I know how far down from the top we're going, at all depths along here, it will have the same pressure, which will equal the pressure down here. Will equal this. You'll be able to compute it this way. And so we're only really interested in how depth changes in order to find out how pressure changes. You will absolutely need to know this relationship in your recitation on Wednesday. Because there we'll be talking about what's called the buoyant force. And the buoyant force is just, if we look back at that picture, it's just, let's look at the force due to the pressure on the top and the force due to the pressure on the bottom, and rather than considering them separately, what happens when we consider them together. All right, we'll see you in class.